Hi guys, continuing from the previous part, we're still on the topic of characteristics of measurement systems. So I'm going to talk a bit more on the dynamic characteristics. So let's talk about damping. So a damping slows the transient response to an input change, which means if I have an input like this, and because due to damping, right, it does not give you this does not happen is because of damping, but this would happen or this would happen, which means it slows the transition time of the system when there's a change in input. Okay, let's talk about a zero order system, which means you have no damping response, which means it would follow the input response without delay. There's no damping, which means if you have input like this, your output would be almost immediate, which means there is no damping. Okay, one such thing that you can think about is actually a resistor divider, which means you have your voltage divider. Whatever input you have, you get an immediate output. That is for a zeroth order, which means zero order system. What about the first order? First order, you have a typical response of what, if you remember the RC circuit, which means you have a charging curve. Okay, this is a very typical charging curve. Okay, so when we talk about first order responses, we need to talk about the rise time and the fall time. So when we talk about rise time and fall time, rise time takes arbitrarily, say this is your 10% and this is your 100%, and we have the 90% top here, and you have your 0 here. So what it does is the rise time is take the output for the output to rise from 10% or to the 90th percent of the final value, and the fall time vice versa. Okay, so another thing that we have to talk about is the tau. Tau is otherwise known as the time constant. In a simple RC circuit, you can calculate the tau by taking the value of the resistor. You take the value of the resistor and you times it by the value of your capacitor, and that will give you the time constant. So in one time constant, it is the time taken for the output to rise to 63.2 of its final state, which means we have to find the final state first, or the final value. Then we calculate a 63.2% of the final value. So if the final value is at 100%, you find the 63.2%. This is the magical number that you have to remember. And that would be for one time constant. So in another tau, or in another time constant, it would rise by another 3.2, sorry, of the remaining amount. So it would rise out to here. So in order to find the steady state value, we not often use 5 tau. So there are a couple of magical numbers that you have to remember. 63.2% and 5 tau. This is the gist of this thing about time constant and final value theorem, the final value. Next, we talk about second order system. In a second order system, you have two energy storage elements, which means you have either two capacitors or you have inductors, but you must minimally have two of them. And in that case, your differential equation that is used to describe this thing, this system, would have d2y over dt squared. For example, when we have that, we have this thing called damping. And we need to look into this thing called damping factor. Okay, so if it's overdamped system, it is actually represented by this very, very slow moving output. So this is very slow. Critically damped is what I label it as almost perfect. Okay, almost perfect, which is this part that I just highlighted on the screen in a kind of a dotted manner. So this is 90. Nice looking output. And you have the underdamped, which is the erratic one, which means underdamped would have some sort of wavy kind of output. Okay, so how do you classify overdamped? Overdamped, so you have a value of 1 on a scale here. Here, it's what we call the critically damped. So anything, say this is 0 and this is infinity, for example. So between 0 and 1, because it's under it, so it's under there. So if it's more than 1, it is over there. And only at 1 and only 1 would you call it critically damped. Having said that, we're going to check. Since we have this kind of curvy, wavy little lines, we're going to talk about how are they going to settle in the matter of time. We're going to talk about settling time. So settling time is the time the system takes for the output to change or settle down to acceptable value. So in this case, you have an input, for example. The input is here, where my red line is. Just for example, okay? So within the final value, this is around the final value. As long as it's within the error band of, say, 2% or 5% of your final value, we accept that, because actually you will never ever get a very straight output. Sometimes it will vary a bit, as I've drawn on the screen, and hence you will never ever get a very, very strict value. Hence, we will have to give it a bit of tolerance. Okay, a bit of tolerance here, say 5 or 2%, and that would actually mark down the time whereby it's within the acceptable error band. And the response time, right, it takes to react to a input stimulus and reach its final value. Okay, so this is the settling time. And the response time will take slightly longer than the settling time. With that, let's talk about the reading in hysteresis. Hysteresis is the incremental input needed to change the output when the input signal changes direction. Okay, so when you have a input, output of a system with hysteresis actually lags behind the input, which means when you give a input signal in this case, you see that your output actually is much slower because at time 0, that is when the response started. It's only at this point in time that your output has something. So there is a bit of hysteresis. Okay, so the input, let's take for example this one. The output changes to +5 volt when the input signal increasing and goes to 20 volts. So once it hits the 20 volt mark, 20 millivolt mark, then you will see a response. And the output will only drop back to 0 when it's below 15, which means when it drops by 5 millivolts, then you will see a change in the output. So in this case, how do I calculate the hysteresis? Is actually get your input signal to change the output. Input signal, so change in the input signal will give you a change in the output signal. So that would be your hysteresis. And that I conclude this part of my